Thanks a lot. Indeed, my name is Mattia. I'm a data scientist at PacMed, and today I would like to tell you about the benefit of doing external validation. That's using a data set which is different than the one you use for the model development coming from a different domain. And yeah, we work with medical data, so for us, different domain normally means a different hospital. And if you were at the talk in the other room right before lunch, then probably some of the things that were discussed there, you will also recognize them in my talk. I would like to give you start with a little bit of a context. So you already have your model that has been trained and you're relatively satisfied with the performance. And then you want to move to the next phase, which involves implementation or probably selling the model also to a different client, a new client. And all those scenarios involve using the model to a data set that is different than the one that you've been used for the development. And there's no guarantee that the very nice performance that you had also applied to the new data set. So I didn't want to be super precise by giving numbers yet, but this is the situation that we will have. Good performance if you just use your own development data set, both for training and testing. But then if you want to test it on the new one, the performance will likely drop. And well, what we would like to address in this talk is why this happened and which are the techniques that can be used to solve this. They fall broadly under the common umbrella name of domain adaptation. The goal is, of course, to get back over here with a good performance. And in that case, if you manage to do that, then domain adaptation will have handle you a new version of your model, which is at the same time more flexible, but also more accurate. And for us, accurate means safer for patients. The other very nice benefit of doing external validation is the fact that healthcare is quickly warming up to the concept of machine learning, and there's a lot of more scientific papers that are published day by day, trying to use machine learning to solve clinically relevant questions. However, there's still quite some challenging to have those models leave the pages of a scientific journal and actually being implemented in practice. As of this summer, only 46 of those machine learning algorithms are actually been FDA approved. And well, there are many reasons for this. One of them is that those models are not flexible enough. They cannot be transferred. So the process that I mentioned before of external validation, if you try to start to consider it as a standard and common step in the process of model development, that will bridge the gap between development and actual implementation. So I decided to split my presentation in three sections. In the first one, I'm going to tell a little bit about PacMed, and especially one of the models that we've been developing called PacMed Critical, and that will be our use case for the rest of the presentation. In the second part, I'm going to dig a little bit deeper in what I mean by domain adaptation and present some of the techniques that we experimented with. And then in the last part, I'm going to show you how this technique will benefit the case of PacMed Critical. So yeah, let's start. In PacMed, we combine machine learning with medical expertise to provide tools, algorithms, that can support physicians and doctors in their day-to-day decisions. Our goals are to have it so that patients only receive treatment that actually improve their quality of life, that every doctor can learn from the decision that the other colleagues make, and then at the end of the day, the already reduced budget devoted to healthcare is actually spent more efficiently. We have different projects going on right now in different areas of healthcare, going from oncology to triage to primary care. Today I'm going to tell you something about the intensive care unit of a hospital. The patients that are admitted to the ICU are in a very critical state, and then it's the job of the intensivist, of the doctor there, to stabilize the patient so that he or she can be discharged to a lower level ward. And the problem is that approximately 5% of those discharged patients, they then die or are readmitted to the intensive care within 7 days of the discharge. These have, of course, negative outcome that could arguably be prevented if you delay a little bit the moment of the discharge. And that's what PacMed Critical wants to do. we want to use all the data gathered from patients during their stay in the intensive care unit to predict what's the probability for that patient to either come back or die if you were to discharge that patient right now. And just for simplicity, from now on, I'm just going to say probability of readmission, but what I really mean is either readmission or death. And then we provide this probability, this prediction probability to the doctor so that he or she can take that into account on whether to confirm or not the decision to discharge the patient. This is a project that started 2 years ago with Amsterdam UMC. They provide us 14,000 ICU admission with historical data from 2004 until 2017. This is a list of all the signals that we are including, so not just patient demographic like age and sex, but basically everything that is measured during the intensive care, the stay in the intensive care. So vital signs like heart rate, respiratory rate, blood pressure, clinical observation like the level of consciousness, all the lab results that are taken, all the procedures that are performed like intubations or renal replacement therapy. Of course, there's a lot of stuff, as you can see, and you should take into account the fact that some of the machines that are always connected to the patient, like the bed monitor, they measure and gather data with a frequency that can be as high as 3 times per minute. So you end up with a very large amount of data. There must be some step of feature engineering. And the way that we do it is like this. Imagine this is the evolution of heart rate measurement for a patient. We bin it, we define time windows of 24 hours, and within one of these windows, we compute 7 feature aggregates: the mean within 1 day, the standard deviation, first and last measurement, minimum and max, and then how many times this thing has been measured. And we do this for the first 24 hours, assuming that this is a good description of the status of the patient when he arrives at the intensive care, the same for the last 24 hours, and then over the whole admission. And these are the features that on which we build our model on, which at the end performs quite well. We have an AUC of 0.8, among the highest one of the highest among the other algorithms that I find in the literature with a similar functions predicting readmission. So then we were very happy with this and wanted to move forwards. That's when we encountered this problem of an external validation. We actually did this exercise twice with 2 different new data sets. I'm going to call them the target data set, while the PacMed critical, the one used for the development, is going to be called the source data set. So the first validation is actually done on the same hospital, but it accounts for the admissions after 2017. In 2017, they started to implement a new electronic patient data system called EPIC. So this first target dataset will include only the admission, around 3,000 admissions, after the new system has been launched. And changing an electronic patient system in the hospital is quite a change. So you can really think of it as a completely different hospital. And then the second, well, if you do that, by the way, I should mention, if you only blindly apply PacMed critical to the new dataset without doing any retraining or any retuning of any sort, then your performance goes down to 0.76. The second validation will be done with data from a completely different hospital. This is 13,000 ICU admissions coming from the Elisabeth Svestede Hospital in Tilburg. And well, if you do that, if you apply PacMed critical to that new dataset, the drop is even more significant. You go down to 0.69. So why is this? What's going on? Well, the first thing that we did is not really anything particularly fancy or any statistical trick. It's more something that has to do with the common practice in machine learning. We basically just took, for each of the signals that we measured, we took all the measurement that was gathered for one specific hospital and plot their distribution and overlay that with the same distribution for the other hospital, for the new hospital, to see if there's any discrepancy in those distributions. And it's a very cool method and very simple method to spot simple mistakes and imprecisions. Things like the fact that the same feature, the same signal is measured with different units in the 2 hospitals. Or we also realized that we had to align our categorical features. Some of these things that were in the slides before, they are registered as categories, as strings. For example, the quality of the cough. But the possibilities of these features, they can be just 2 in one hospital, good or bad, or 7 or 8 in another hospital. So when then you took this and dummified them and transformed them into binaries, there is no alignment anymore of those features. So this is something that you should do. As I said, this is very simple. To be honest, we probably should have done this even at the very beginning of the project and not after having noticing the drop in the performance. But with so many features to handle, maybe it's not a surprise that some of these things can slip through the cracks. But it was also very interesting to start discussion with our collaborators, noticing that indeed there are some things that are still different even after these sanity checks, let's say. For example, we noticed that there's a very big difference in how many times the two hospitals measure lab results. And this was quite worrying for us because how many times you perform a specific lab test is one of our most important features. And noticing that is very different between the two hospitals was, as I said, worrying. But then we realized that indeed one of the two hospitals had daily, routinely batteries of tests that they do just every day, while the other one, the doctor has actually to order the different lab results, and that can explain the difference. All of these things that has to do with a different distribution in your features is called covariance shift. It can come from a different patient population or different structural practices in the offices, like in the hospital, like what I just mentioned about the lab results. It basically means that while you're training on your source model, the source doesn't see as many examples that are similar to the one in the target model. So then when you test it on the target, you're bound to make some errors. And this is indeed something that affects also our case. And to convince yourself of that, you just have to notice that at the Amsterdam UMC, 55% of those admissions are cardio patients, while the number is less than 10% and ATZ. So there is certainly a different patient population. How can you solve it? You can do importance weighting, meaning then while you're training on the source, you give more weight to the examples that are more similar between source and target. There is one additional thing that can go wrong called concept shift. And in this case, what changes is not the distribution of the features, but the relationship between the feature and the outcome. That's actually that's the thing that you want to model. So imagine that you train your model on the target set, you manage to reproduce one specific dependence, then you move to another hospital and have a different one. Again, you're bound to make some mistakes on the target set. And well, an example of this phenomenon is what I told you before about the number of lab results. We were not surprised to notice that this was one of our most important features, because if you think of it, a doctor orders a lab results when he or she thinks that the patient has something wrong. So it's reasonable to see that number is related to the outcome. But of course, this is only true if those lab results are not done routinely every day. Then that relation with the outcome is completely disrupted by taking away the component of the actual decision of the doctor. And another example is what you see here. The two distribution shows the distribution of one of our features, doesn't matter what it is, in one of the two hospitals in green and the other one in orange. The fact that the two distributions are different, that's the covariance shift in the previous slide. But here you also see how the outcome depends, how the outcome changes as you move as a function of those features. And again, you see the two lines are clearly different. So manifestation of the concept shift. How can we solve it? There are different possibilities. The first one, well, you just put the data together. You train on both target and source. This indeed will probably lead you to a big improvement in the AUC. There is one problem, and that's to do more with the legal side of things, because in order to have that, you need the two datasets to be actually present in the same point, in the same place, and accessible by the same user. And normally, hospitals do not really like to share data. We, for the moment, we're not allowed to do this. So alternatively, what you can do is use sequential model, where you train your normal model only on the source. This is your normal loss function. And then you export the knowledge gathered by on the source to the target by training a new different and separate model, adding an additional term here when that is a regularization term that penalizes any difference in the coefficients between target and test. So in this case, the two datasets do not have to be present in the same place. You're training two different models, and you're only transferring the knowledge of the model encoded in the coefficient. So this is okay. One of the problems, however, is that in this specific flavor of sequential model, you can only do it for a linear model. If you want something that can only be applied for nonlinear models, then you can do something like this. Again, a sequential model, but now you train your model on the target and then transfer that information to the source by including as a feature the predicted probability of the target model. Again, the idea is more or less the same as in the previous slide. You're trying to model deviation from the source data set, and you're not required to put the data together. Another alternative, the last one that I'm going to mention today, are hierarchical model. So in this case, we have a different set of coefficients for each domain. They are written like that. So there is a part that is common, and then one that is more domain specific. And then you train on everything, both target and source together, each one with their own set of regularization terms. And the benefit, there are a lot of benefits for this class of models. One is that you can not just include two domains, but have a whole hierarchy of domains. The other one is that this is very easy to encode things like the concept shift, because now every signal that we measure will have its own set of coefficients that are domain dependent. So the same features can have different effects in different domains, in different hospitals. And another benefit is that you can encode it. You can encode some kind of medical knowledge by putting some priors on the regularization terms. However, as in the very first solution that I told you, now you are training on source and target together. So there's that. Yeah, let's see what works best, at least in the case of PacMed Critical. So this first slide show you the results of the first validation that we did, so the one before 2017 and after 2017. We were starting from around 0.76. That's the first column on the left. If you forget everything I just told you about domain adaptation and just train a model on the target data set, then that's the second column. It doesn't get you much further, just a small improvement. But then if you do implement the technique that we discussed right now, you see that you can get to very high values. It's similar to what we had at the very first slides. Then the second validation, the one between Amsterdam UMC and ETZ. So in this case, we were starting even lower, around 0.7. In this case, if I forget about domain adaptation and just train a model only on ETZ data, then I do see a big jump. I get already as up at 0.74. However, well, this model will have the same problem that PacMed Critical had at the beginning. It's not transferable. It will only be, you can only apply this to the patient in Tilburg on ETZ. On the other hand, you should prefer solutions that involve domain adaptation, like the one that are presented here, because it makes your model more flexible, and also you gain a little bit more of accuracy. By the way, I'm not showing you the other two bars there, because those are the technique, the algorithms that require to train on both target and source, and we're not allowed to do that, as I said. So I was a bit surprised when I saw these results, especially because they seem so different in the two exercises that we did, especially in the second column. The effect that the difference that you can see by training only a model on the target. And then I suspected that was due to the fact that the two data sets are so different in size. The one here, the target only has, well, less than 300 new admissions, the ones after 2017, while in this case it's 13,000 admissions, or the same size of the source data set. And so to confirm this hypothesis, what I did was check the evolution of the performance over as the size of the target set increases, and that's the result. So on the x-axis, you see the number of examples in the target increasing more and more, and on the y, the performance, the AUC. The orange line is the model trained only on the target, that as you increase the number of observations, slowly climbs up. But if you do domain adaptation, then you see that you already have an advantage already from the very beginning. Still with only 1,000 admissions events, you already have a very high level of performance of AUC. So I stop at 3 around the 2,800, which is where we are in the first case that we consider. But if I extend the axis, then the model developed only on the target will have still kept rising until reaching the performance of the techniques with domain adaptation. And that's how we are with the second validation, Amsterdam, UMC, and ETZ. So that's the reason why, in this case, the domain adaptation, they are not adding as much as they were doing before, which to me suggests that all these techniques, they are certainly more viable if the target data set is smaller. And that's pretty much it. I want to summarize my conclusions. Well, the first and most important fact is that indeed, domain adaptation, we think is an important tool to make your model more flexible and safer. For us, it certainly benefited. The PacMed Critical now it can be applied to a larger set of patients and making it also readier to actually be more closer to be implemented in practice. These techniques, they certainly work. They are more beneficial if you want to use a target data set that is small. And among all the ones that we consider today, the one that rely on sharing the data among hospitals, they add more value than the other one. So if you can do it, then you should certainly go for those. But even if you cannot do that, then things like sequential models are certainly still certainly beneficial. So yeah, thanks for your attention.